Should I start sharing my screen now?
That would be great. Thank you.
Can you see the screen?
Yes.
Yes.
Should we start?
Yeah, why don't we go ahead? It is 12 o'clock.
Okay, so now I will continue with secret sharing based techniques. So previously we discussed encryption based technique. They are computationally secure, means an adversary having enough computational capacity, they can break the underlying technique so that they can know the secret. On the other hand, information theoretically techniques are secure regardless of the computation power of the adversary. Even if adversary has unlimited amount of power, the computation capability, he cannot break it. So these techniques are also, that's why quantum secure. So first, just recall that, okay, what is secret sharing? So suppose if I give you 1 point and ask you how many lines you can draw using 1 point. So the answer is you can draw an infinite number of lines. But now what will happen if I give you 2 points? Then you can draw only one line from these 2 points. So whenever this line passes the y-axis, this will be the secret. And now you place your secret at this point, and these two red dots, the point that I gave you, they will become the secret shares of the secret. So suppose Alice wants to share a secret with Bob and Carl. So Alice selects a polynomial, any random polynomial. So here she selected 5 plus 1x, and now she will place her secret value as the value of x, and whatever value he will obtain, she will give it to the Bob and Carl. And if Bob and Carl will not communicate with each other, they can never know what is the secret of the Alice. Now here, two impact we need to note down. The first one is the impact of the degree. So here in the polynomial, Alice used polynomial of degree 1. So how much will be the polynomial degree should I use? So if I know f servers can collude, then the polynomial degree should be f plus 1. And in case that if no server will collude, that all the server will remain isolated, then the polynomial of degree 1 is enough. Since we use multiple servers, that's why this is also fault tolerant.
Shantanu, it looks like you're having some bandwidth problems.
Sorry? Can you not hear me clearly? Hello?
I can hear you actually. This is Murat.
Murat, can you not hear? I didn't understand. Can you hear?
I could, but someone couldn't hear, I guess. Can you speak up?
I think Ken was having some trouble. I could hear him clearly.
Me too.
Okay, let's try. Yeah.
Some people are writing on chat also. Abdul is saying that he can hear. Okay, so if I continue, if you don't hear, please let me know. Okay.
Yeah.
Where is he writing? I don't see it on the chat.
I don't see it on the chat.
Maybe Abdul wrote in private chat to me.
Okay, let's. All right. I'll tell you what. I'll do one thing. Why don't you present? I'll monitor both the chat and I think Vana is saying she can hear well. So I'll monitor the chat and Slack and we'll see. Okay. I'll stop you in case I need to. Okay. All right. Go ahead.
Okay. So these are the two factors that are related to the secret sharing. So now, suppose how can I use this secret sharing technique to create the shares of the shares? So any number of servers I can use, and I can create shares of the my secret using a polynomial and send to several servers. So here I send my share to 4 servers using a polynomial of degree 1. And secret can be reconstructed using the Lagrange interpolation. Since I used polynomial of degree 1 and I did not perform any computation, so I can get shares from any two servers. So in this example, I am taking shares from server 1 and server 2, perform Lagrange interpolation, I will get back the secret. I can also get from other two servers and they will give me the same answer. This was the basic of the secret sharing technique. So there is another technique in this is similar to the order preserving encryption. So they introduced order preserving secret sharing. This is by Devikant Agrawal. So here they follow the same idea that you need, if there are two values, A is less than B, then in secret share they also need to follow the same rule. And this is good for the maximum finding or minimum finding. You can classify secret sharing techniques into two categories. One is where servers communicate with each other, in which we have systems like Jana, ShareMind, and Conclave. The another classification category is non-communicating server, where server compute your task, but they will never communicate with each other during the computation, before or after the computation. So whenever the server will communicate in the first category, communicating server, so they will create significant overhead. So we will focus on two things. One is obscure, that is non-communicating server, and one is the conclave that require communicating server. So first, see what is the advantage of secret sharing in data outsourcing. So suppose I want to find the answer of the sum query that selects some salary from employee. So since secret sharing is additive homomorphic, so if I add any two shares in at the cloud side, and whatever output I get from the addition of the shares, and if I interpolate them, I will get the real answer of the addition of the two real numbers or multiple numbers. So by this way, I can add anything, add any integers very easily. But now there are challenges. Except addition, we cannot do anything with secret sharing. So there are things that how we can perform the aggregation queries with complex selection, while we want to also hide the access pattern that the tuples that are satisfying the query. Then another thing is that we want to also execute the complex selection criteria like conjunctive queries, disjunctive queries. We also want to do the join queries using secret sharing. This is the paper by Devikant Agrawal, and they wrote the thing that in this case, the database owner need to remember the polynomial. So in the figure, you can see that there are 10 values. So 10, 20, 40, 60, and 80. For these values, whenever they are creating secret share, they need to remember all the polynomials that they used at the time of data outsourcing forever. If they will forget any polynomial, they cannot execute the query. So they, at the time of data outsourcing, they can use some polynomial, place the value, and create shares. So here they created three shares at DAS1, DAS2, and DAS3. Place them, and whenever the query will come, so suppose the query will come for value equal to 10. So they use the same polynomial they used. Create the share, go to the cloud, and cloud will find the exact answer. 210 is from DAS1, and it will send it to the user, and user will interpolate and get the answer. So in this case, the major problem is this. The first major problem, user needs to remember all the polynomials. This is but on the other hand, this is very fast. On the other thing, that it is revealing access pattern, that you are directly touching one row, whatever rows are satisfying the query, and sending it to the user. And if multiple rows are satisfying the query, you will also reveal this thing, okay, for value 10, how many rows I am sending, and for value 1, how many values are sending. So you are revealing the distribution. So this was the problem. So now question is this: is there any technique that where we don't need to remember, means the database owner doesn't need to remember anything regarding the polynomial? Just it will take one polynomial, create secret share of the data, and outsource it. And after that, it will forget everything. So we need this type of technique. And another thing is that since we want that cloud will search on the data, so we need a technique. The answer is we need a non-interactive string matching operation for the cloud. There is a technique, this is very recent technique in theoretical computer science paper. So what happens in this paper, they represent the data as a unary vector and then create secret share. So Suppose my dictionary contains only three symbols A, B, and C, and I make this rule. If A will appear, I will make a vector 1, 0, 0. If B will appear, I will mark as 0, 1, 0. And if C will appear, I will mark the third position as 1 and the remaining two position as 0. So these are the bit vector or unary representation of three symbols. I will send it to the black box. Black box means it's a set of polynomial, whatever polynomial you are randomly selecting. But the important thing, all the polynomials should be of the same degree. If you are changing the degree of polynomial, it will create the problem. Then you need to remember something. So all the polynomials of the same degree, you will get the secrets here, and that's it. You will outsource the thing. So now, how will you outsource the data and how you will search using the string matching technique. So this is the database owner and there are three servers. So let's say I want to database owner wants to outsource the value B. So first he will write the unary representation, then select any random polynomial of the same degree. So here he selected three polynomials of the same degree and place the value that is 0, 1, 0 on the polynomials and get other values 5, 10, 2 and for the server 1 and it will outsource. So note that here, for example, if you see the server number 2, server 2 is holding value 10, 19 and 4. So server 2 cannot know, okay, what I am holding, but it is actually holding the secret of the value B. So this way we are hiding the actual value from server. So now how we can search using this string matching technique. So suppose the user also wants to search for the B. So in this case, user will first represent B as a unary vector, create random polynomial and place the value and get some secret value. So now note that here that the shares value at the cloud side, at the user side, that the polynomial that he is using and the polynomial that database owner used, they are different. So there is no need to communication between the user and the database owner. So if user knows the degree of the polynomial, he can search whatever he wants. Now note down the second middle box in that color. In this case, server is holding the values outsourced by the database owner as well as values outsourced by the user. Now see the server number 1. Server 1 is holding 5, 10, 2 and here it is holding 1, 3, 4. By observing these values, he cannot know are you searching for the same value that I am holding or not. So this is by this way it is hiding the data query and whatever is the operation will be. So how the operation will go on. So the vector v1 is representing the database and vector v2 is representing the query coming from the user. We need to multiply these things bit by bit. After that, we add all the values. So after addition, we get 43, 147 and 313. Send these three values to the user. User will perform using Lagrange interpolation, and if he will get 1, he will know, okay, the value B is there. If it will get 0, means the value B is not there. So by this way, we can execute the string matching operation at the cloud side. And note that the cloud is sending only one value. So the communication cost is very minimum. So now the question is this, can we use this string matching techniques for executing selection and aggregation queries? So this is the our paper that in this paper we did complex selection queries and here server do not communicate as this is using the same string matching technique. So database owner need to work with the query execution. In addition to this, we also included methods for result verification for all the queries. So count, sum, maximum, minimum. And the most important thing that is this, we can support multiple database owners. So suppose here IBM and Google, they are outsourcing their data to same number of servers and any user can create execute the computation on this data. There is no need to do any special technique. So we can support multiple database owners. So first thing is how we can outsource the data, and then second thing, how we can execute the aggregation query. Suppose this is the relation, employee relation, and I want to outsource using secret share. So I create first two relation. One is E1 and one is E2. So E1, the first three column of E1 is same like the original relation. Now I add two additional column, TID and index. In TID, column, I wrote down the any row ID, tuple ID, and the index value is also same. So you see the fourth and fifth column, they are having the same value. Now on E2 part will contain only that column on which I want to execute the maximum minimum query. So if I want to execute maximum minimum query on the salary part, so salary column is also here, but there may be a problem that I want to fetch the entire tuple based on the maximum salary. So I cannot join these two tables. So in order to do this, I use the same index value in the E2 also. So see the first row, 5,000. This value is also having the third row in E1, E102, Adam 5000. So the TID value and index value, they are same, just like the first row of the E2 row. So for E2 row, I use the order preserving secret sharing on the salary column because I want to perform the maximum operation on SSTID column and entire E1 table. I use the secret sharing using string matching technique. In addition to this, in E1 column, I add some more columns. These columns are useful for the verification that server is not deviating from the computation. Even I can, without this column, I can verify the result because I am using multiple servers. If I want to verify, I can use any Byzantine protocol, but still there may be a chance that if there are 100 servers and 100 servers are created by some company and they have a bug in their server that whenever they see the fifth row, they will eliminate this fifth row to processing. So we can verify this kind of thing, while Byzantine protocol cannot verify this. Okay. So how we can execute the count query? I will give you only example of count query here, while it can support maximum minimum sum query. So suppose the query is this: I want to count the number of people having name John and salary equal to 1000. So first here you will see whatever operation I am showing you. This is written in the clear text, but in at the cloud side, this always be in secret share. So for the purpose of explanation, I am using clear text data. So here is the name column at the cloud side and the salary column. Now the green box is showing the query predicate by the user. I will perform the string matching operation. As the string matching operation will execute, it will give me the value 1 and 0 as you saw in the previous slide for the string matching operation. All these values are in secret share, so the adversary cannot know which value is 1 and which value is 0. The same operation I perform on the salary column. So based on doing this computation, I find the name of people, John, and salary is 1000. But now I want to perform the conjunctive operation. To perform the conjunctive operation, I perform multiplication of vector v1 and v2. So here I perform the multiplication. After multiplication, I get only one vector. This is 1 0 0 0, and I add all the values. After addition, I get
So
value.
you have to send entire bit vector size of the entire database each time.
No, I need to send the bit vector of size my query predicate. So suppose here is the query predicated John. So I need to send the bit vector, the user needs to send a bit vector of size John and bit vector of size 1000 only. So
But
even
what about this multiplying vectors? These vectors needs to be exchanged between the
no,
servers, right?
I am not exchanging vectors with the user. Vectors always stay at the cloud side. So cloud is performing all the multiplication. So this operation, so see here, this is the user send John and John. So after this, here the cloud perform the string matching operation and get this values 1100. So this operation is computed at the cloud side. Entire vector will stay at the cloud side. Okay. Now the salary for the salary operator, salary column, the cloud will perform the string matching operator and it will get vector v2. And now these two vectors will stay at the cloud side. But now, since my query is the conjunctive query, these vectors are not giving me the final answer. So cloud will also multiply these two vectors. So after that, cloud, after multiplication of these two vectors, cloud will get 1000. This is the again the size of the database. But now since secret sharing is additive homomorphic, I can add all the values. Whenever I will add, it will give me the only one value. And this is the final answer. So I will return only the one value to the user, regardless of the database size.
But still, in order to do this matching, string matching operation, you have to send a vector of entire size. Anyway, we'll take it offline. So I think, anyway, continue this way.
Okay. I will email you to discuss. Okay. And so now by this way you can get the answer. But here is a problem that whenever you perform the multiplication will increase the degree of the polynomial. So suppose if you don't have so many shares, can you do the computation at the cloud side or not? Or you will never get the answer. So we can still get the answer even if the degree of the polynomial is increasing. So by increasing the number of communication round, in this case, we will increase the communication round between the user and the cloud side. So I will show you. First, see the security guarantee of this approach. So what is happening? So this is completely oblivious because I am executing the identical operation on each row. So that's why it is completely oblivious. The adversary cannot know anything based on the operation. No output side because at the end of the entire computation, cloud will send only one value. By sending only one value, he can never know how much values are satisfying the query or not. So now previously we saw the query for two predicates. Now see the impact of the share. Suppose I don't have enough cloud. What can I do now? Then it is a problem. But when we did experiment, we found that it is not still not a significant problem whenever we are not having enough number of cloud. If we have enough cloud, this is very good. So suppose the query is count number of employees whose name is John, salary equal to 1000 and age equal to 40. So here, see, I am having three predicates. Whenever I multiply three predicates, the degree will be 4. So I need at least 4 shares. Okay. So vector v1 is representing the string matching operation over John name. Then v2 is showing for salary and v3 is showing for age. Now, if I have enough number of share, I will multiply these vectors and add all the things, get the final answer 1 and send to the user. But now suppose I don't have 4 cloud. I have only 3 cloud. So what will happen? In this case, I can still multiply only 2 vectors, v2 and v3. So after multiplying v2 and v3, I will get v prime. So I will send v prime vector to the user and v1 vector to the user. The user will first perform the interpolation, then it will multiply and it adds. So this is the thing that if you decrease the number of cloud, the user needs to perform some computation at his end also, and the communication cost increase. And if you have enough servers, you don't need to do the entire computation at your end. We can do also maximum query by this way. So in maximum query, suppose first I find the maximum value, because since here values in E2 table is in order preserving secret share, I can find okay which is the maximum value. Based on this, I will get the SST ID, means secret share tuple ID, on which I can perform the string operation. The entire table E1 is in the form of string matching secret shares. So based on this value 2, I will perform the string matching operation on 2 versus the TID column. Whenever they will match, I will get the real answer, the real tuple, and send it to the user. Based on this, we will get the answer of this type of query. Now see how it works. So we compared this thing with one of the existing system, MPC system developed by one company. So they are doing MPC, means in their server, they are communicating with servers are communicating with each other. So that's why they are not communicating during the computation. Whatever computation they perform, they send their data equivalent to the size of the database to the second server will send to third will send to 1, and this will continue multiple rounds. So their performance, they will take a significant amount of time for doing the same operation, and we can do in significantly less time. This is the final conclusion for this thing. If we have 6 million rows and we want to do these types of queries like aggregation, count, sum, maximum, minimum, on 6 million rows, it will take at most 50 seconds. And this is much better as compared to downloading the entire data and do the local computation, encrypted downloaded data. So I means that you download the entirely encrypted data, decrypt it, and then execute the query. as I told you in beginning slide that it can perform also the result verification, but I am not showing the approach of the result verification. But here is the results of the uh, result verification technique. It is not creating significant overhead, but yet some overheads are there. So the bars in the red and the light red color, they are showing the without without and with verification part. So the first part is the without verification and the next part is the with verification. So now you saw that Obscure can support multiple database owners, but here the thing is that all the database owner needs to outsource the data to the same server, and then you need to read the entire data. So if there are 1 million rows by 5 users, so you need to read the 5 million rows and then you can give the answer. So how we can avoid this type of thing? Can we reduce the computation cost at the server? So the answer is yes. If we do some local processing at our side, then we can do it. So this is the paper called Conclave. They propose this system. So suppose the query is this: I want to count the department-wise number of employees earning $1,000 across 3 databases from UCI, UCLA, and San Diego. So the trivial solution, as I told you, that if they will use any existing MPC system, they will send their 1 million rows. On 3 million rows, MPC system will execute the task and it will give you the answer. But this is significant overhead. And what the trivial solution will do in the black box? First, it will scan the all the things, then perform union operation, sort, group by, and project. So these all the operation will go on at the MPC side. We can avoid doing so many complex tasks at the MPC. So, and this is the disadvantage of the approach, that you are doing everything in the MPC domain. This is the proposed solution by the Conclave. So Conclave suggests that you can avoid doing most of the computation at the in the MPC domain and do your computation at the local side as much possible as you can do. So here they are filtering the tuple based on salary, sorting, group by, and projecting all the things at the local side. Based on this, all the database owner will get their corresponding tables, table T1, T2, T3. And then they send this significantly smaller size table to the MPC system. And then MPC system will do some computation. But note that here, the green box, they use some trusted authority also during the computation. Now, what Conclave is doing. So previously we were doing most of the computation at the cloud side, but now the operation is reduced significantly for group by operation and project operation only. So they are reducing the computation. So this is the thing, that for a query, they reduce the amount to be pushed to the MPC domain using push up and push down operators. So they propose several operators. First one is for the join, they are saying hybrid join. Hybrid joins means whenever they use a trusted authority for sorting the data based on the key, they call it hybrid join. Public joins means if the joining column is in the clear text, this is called the public join. Hybrid aggregation means again you are using the trusted authority for doing the join aggregation operation.
Just a clarification. So in Conclave, unlike your work, they are doing distributed processing. So each site has its own data that they execute on query. Unlike your setting, you outsource one data to multiple servers.
Yes.
Okay.
But 1 minute. Here, in their case, they have their data, but they are also outsourcing to multiple servers.
So the data that they do local processing is secretly shared?
They use any existing MPC system. They don't specify any specific MPC system that you need to use only this specific MPC system. So the thing is that you can push the operation, some part of the MPC computation to the data owner, and whatever computation he can do it, you will perform the computation at the database owner side and then push the final output to the MPC domain. And MPC domain is running in multiple clouds.
Okay, thank you.
Yeah, Murad, they're using MPC as a black box.
Yeah, but basically the setting is slightly differently. So it's like pushing the predicates to each local site or whatever.
Yeah, so they're pushing it inside that's correct.
Main problem is this: they use trusted party. So this is the main problem. So see here, This is the result of the conclave. So ShareMind, this is a very famous system by some European company. So if you use ShareMind for the join operation, only ShareMind, so the time is increasing significantly. But now if you use Conclave, hybrid joins, means you are using some trusted party to perform some part of the join operator, then the time is reducing. And if your column, the joining column is in the clear text, then public, this is called a public join. In public join, the time is significantly less. This is because of the trusted party. So the question is that how we can avoid the use of the trusted party. Now I'm not going to the details of how we can avoid this thing. Is there any way or not? Even the paper is not suggesting anything that how we can avoid the use of this. So now there are some industrial systems also by different companies. They are working on designing either MPC system or the system that do not require communication among the servers. So these are the names. Because of the time limitation, I am not going, I have slides, but I am not going about the details of the some systems. Jana by Galois, how they are working, and Pulsar, this is LA-based startup company. And this is the some comparison, how we can compare different techniques, secret sharing based techniques as compared to MPC based techniques. As the conclusion part of secret sharing based techniques or MPC based techniques, they are information theoretically secure because the adversary cannot break the data, but they require communication overhead because you are now using multiple cloud. They will communicate or they will send you data. Somewhere there is communication overhead. You can do join queries. There is only one paper for the join query, but this is very extremely n squared thing. So you need to generate n squared data or reveal some information. So join queries are not efficient. Nested queries, they are also not efficient in secret sharing setting. And another thing, they need more than one non-colluding server. This is the end of my part for secret sharing. So now Anton will explain about trusted hardware. Anton.
I'm sorry, Chandu. Can I ask a quick question?
Yes.
If you go back to the industrial efforts, is there one effort that really stands out from the rest? Yes, in this figure.
Can you repeat your question?
So is there one of those systems that really stands out from the rest in terms of the features it provides?
No, so this is, you cannot get all the things that all one of the systems. So suppose if you want to do aggregation queries and while you want, okay, all the servers can communicate, then you can use Pulsar, but it requires, there should be only one table. If you have multiple tables, they cannot support anything. So they require huge representation of the entire data. So on the other hand, Jana can support joining operation, but Jana is very slow in that case while you are having this.
Actually, if I could add to that for a quick second for Shantanu's answer. So I think if you look at, so there's each of these systems offer different features. So for example, Jana, it supports basic variety of different techniques all the way from deterministic encryption to MPC based mechanism. Actually, it's quite nice in the following sense that you can, you have a schema, you can declare in your schema level what kind of encryption technique you want, right? And it'll sort of implement it for you. You can, but they put limits. It's actually built on top of Postgres. So they put some limits. For example, if you want to do a join, if I know correctly, Jana will not do it in an MPC field. It's very, very complicated. So it'll have to be, Shantanu, correct me if I'm wrong about that, but they'll pretty much have to be deterministic encryption at that stage.
Yeah.
But the advantage is it sort of covers the whole of SQL, and it's a very big advantage. Now, Pulsar is sort of very different in focus in its mind. It's like, you know, the Karpmuller's work that I think Shantanu described earlier, like the indexable techniques and so on, the older one. So that's also, this is Rafi's system. It's like the Rafi Ulrich is from UCLA. So he's one of the founders of the.
Right.
So they have very fantastic technologies, but for different purposes. So they have searchable encryption, which is very fast. And there is also something called, maybe Shani, you might want to say 1 minute about this thing, the function secret sharing, if you want to. Just add that, and then maybe that'll give an idea of what that is.
I have slides also for function secret sharing.
Forget about slides. Just tell them what it is.
Okay. So I hide those slides here. So here you saw that only I am using secret sharing only for the purpose of database outsourcing. But Yuval Isai and other people in Israel, they developed function secret sharing technique. So what happening that you want to execute PIR like operation, private information retrieval. So you have one database and you don't want to outsource it. You want to just share this data with someone in clear text. And now on this data, you want to execute the computation. So instead of creating the secret shares of the data, they are creating secret shares of the function. So Pulsar uses this technique also, that data is in the clear text, and now your computation function is in secret share format. And whenever you want to do the thing, they will do now count query, selection, count query, sum, maximum, these types of queries they can do. So in NSDI 2017 or 2018, Tafi also wrote a paper on how we can use function secret sharing technique for these types of operations. So they define all the count query operation, maximum, minimum, how they can do it.
Actually,
Right.
they've also mixed one more thing. They've also mixed MPC. The Pulsar has mixed MPC with function secret sharing, and that's a very powerful sort of situation.
Combination.
Combination. So
Yeah.
different features, I guess. One long way of saying that they're different features.
Thank you very much. Thank you.
Okay, so now Anton. So I am stopping my share screen.
Okay, so let me take over and share my screen here. So can you guys hear me well?
Yeah,
Yep.
I can.
Yes, we can hear you clearly. We can hear you clearly.
Okay, cool.
So, Shandu, maybe you might switch the video off. Yeah, perfect. I'm going to mute myself too.
So essentially, my part of this talk is to explain what SGX is about. So what kind of security it provides, and more even interesting, what kind of security it doesn't provide. So I was trying to switch here to the full screen mode so we can like all see. Okay, so okay, let's start with SGX. So this Intel secure guard extensions, or these SGX enclaves, right? So let's just understand what was the motivation for inventing SGX to begin with, right? So let's quickly review the security and isolation in our systems, which were running for at least like last 5 decades, right? So typically we run a small piece of software, which we call kernel, operating system kernel, this yellow piece here, right? So it controls access to hardware, and then it creates something what we usually run as users, right? So like our programs like databases here, web browser and stuff like that, right? And so, okay, sure, everything was fine for a while, right? We know that privilege levels, they protect the kernel from user accesses. This is how the kernels were designed in like early 70s in the last century, right? So the user cannot really access the kernel memory. That's kind of like operating systems 101, right? And then, you know, the page tables allow protection between the individual user applications. So the user cannot access memory of another program, right? So everything was fine, right? So, and we had mechanisms for controlled access, essentially controlled communication between user programs and the kernel, which we know they're called system calls, and between individual applications on your machine, right? So some inter-process communication mechanisms, right? So the world was good. So it was invented, as I was saying, like here I still say 40 years ago, but really it's like 50 years ago. And we were using those time-sharing machines back then, right? They were expensive. We have like one machine and just like hundreds of people are using it. But all people were kind of friends, right? So the hardware was expensive, but no one was attacking each other, right? And there's like Ken Thompson and Dennis Ritchie working together on this early Unix prototypes on PDP-11 in 1972, right? The irony is that we literally run essentially the same kernels today, right? So those guys invented them for us with C language 5 decades ago. But back then, those kernels were only maybe like 9,000 lines of code, just a handful of system calls. And today we say, sure, let's just keep scaling. And we took the same C language, the same software development methodologies and scaled them up to those 70 million lines of code of Linux kernel today. And this is the map of the Linux kernel, which features 40 major subsystems and roughly around 3,000 device drivers. And it's a very fast moving system, right? Because there's a bunch of people committing, and there are like hundreds of, like thousands of meaningful commits a year to this Linux kernel. So of course this system became fragile. So multiplied by, you know, unsafe nature of Linux, of C language, bugs and vulnerabilities are just routinely introduced into that code, right? And this is where the problem starts, because, well, we had this graph of Linux kernel vulnerabilities by year, so it was kind of like lagging, like it was tracking in the hundreds in the past decade, but then it's like quickly jumped here, like in 2017, because like exploitation became popular, so it was essentially became kind of a, instead of being a hobby, became a thing you can do for money, right? You can sell vulnerabilities, or you can just, you know, make a career out of it. And suddenly it turned out that this giant 70 million lines of code system is no longer secure, just because, you know, anyone is waiting for new device drivers from, let's say, some company which, you know, builds a new cell phone and pushes new device drivers into the kernel. So they will contain vulnerabilities, because no one really knows how to build secure kernel code, right? And roughly speaking, we're still a bunch of mitigations were like rolled in here, like you know, like you cannot really smash stacks anymore. Everything is randomized, and even some advanced techniques like code pointer integrity are coming to the Android kernel very, very soon. But nevertheless, it remains exploitable. So we still have roughly like 170 kernel vulnerabilities a year. And those are the ones which have CVEs assigned. And, you know, like often kernel developers just say, sure, like I see a bug here, it's clearly can be exploited. I don't even bother. Let's just don't bother assigning a CVE. Let's just fix it and push it, right? So it happens. If you start like looking through the commit logs, you will understand that there are more. Okay, sure. And here Intel comes to the rescue. They say, okay, sure. What's the problem now? Well, the problem is that we don't trust our programs anymore, because if we're running a web browser here and you visit some nicely looking web page, it might actually try to exploit you, right? And while web browsers are also very complicated, 17 or 20,000 lines of code as well, well, exploits are there. And the moment they exploit the web browser, the operating system kernel, which we used to trust, can no longer provide this protection, because, you know, like you can easily find an exploit in a kernel in like, or at least you can pay and buy it, right? So, okay, at this point, you no longer own your machine. And typically you're like, it's a chain of exploits, right? So typically, as I said, like there's a lot of mitigations today. So like, but people figured out how to, first of all, use automatic tools to chain exploits together. And those tools are actually like, they are very, very impressive. They are like compilers which allow you to like program in a specific language, which then is like used for exploitation. And the moment you don't own your kernel, you don't own your system, right? So any sensitive data which you were having here in your other application is owned by the attacker, right? So that's kind of scary. And the high-level observation, which was made probably like a decade ago, that this is not going to change, right? No matter what you do to this kernel, like unless you like completely replace it, and it's not really clear how, because it has to be verified or something like that, but you know, it just verification doesn't scale to millions lines of code. So you can't really trust your machine anymore, right? So the moment you connect to the internet, and sometimes even like air gap machines are exploited as well. Okay, Intel says, okay, we're gonna fix it for you. So how they decided to do this? So they said, okay, sure, right now your trusted computing base is not only the application, but also the operating system kernel. And if you're running in a cloud, there might be another operating system underneath, which is called a virtual machine monitor or hypervisor, right? So it's also exploitable sometimes as large as the operating system kernel. I'm not even talking about some firmware exploits, which are here on the CPU. There is like yet another OS running here, like no one knows about it, not here, but on the chip, right? So Intel management mode. But they said, okay, sure, can we make this TCP smaller? And this is where they started thinking of how to build the SGX, right? So what they said, okay, what if you want to have this tiny secure partition here, which we're going to call an enclave, and the only thing it will depend on is just some piece of silicon or like some piece of logic of the CPU here, right? And then we don't have to trust any of this anymore, right? Because this is out of scope, right? So it's just silicon and this tiny enclave. Even the application itself is no longer trusted, just a piece of application which runs inside the enclave. And I told you that all this, the tower of firmware subsystem, not only the hypervisor, but something like a BIOS, system management mode, are also out of your TCV, right? So at a high level, that's a great kind of design vision, saying, okay, let's just put everything outside and it's no longer trusted. Seems like a way to the future, right? So this is effectively Intel SGX enclaves, right? So the idea was great. Okay, let me tell you how they're implemented physically on your machine. So what you usually have is, imagine you have a memory of your user level application, something like, I don't know, like, again, let's assume it's a database. Well, and typically you have some text section, which is code of your system, right? And some data sections, some stacks will be here as well, right? And Intel said, okay, sure, load will create a tiny partition inside, right? Which will be protected by the CPU. This partition itself, which also will contain will be a simple application as well. So it will have its own code, its own data, but the CPU somehow first reserves this memory and protects it from the rest of the system, right? So essentially, Intel introduced several new instructions in their instruction set. They're implemented as in microcode most likely because, you know, they're complex and it's just like, I don't think there are many, like a lot of silicon changes happened, but you know, at least on the surface, it's a new extension to the instruction set, right? And so what happens here is that you say, well, sure, I start my application normally, and then at some point you designate some memory, say, okay, let's start an enclave, you load some data here, some code, right? And you start running, and this orange partition is completely hidden from the rest of the system. So if the operating system kernel tries to access this memory, well, it's impossible. If the application itself tries to access this memory, it's also not possible. But the enclaves can access the memory outside. So essentially, if you want to bring some data inside the enclave can just read it in, right? So it's kind of clear how it works, right? Okay, sure, and that's like, there are some hardware protections for confidentiality, meaning that all the memory of the enclave is encrypted below the last level cache. So, right, like if you don't follow how the caches are working, so typically you have L1, level 2 caches, and also like depending on which machine you're running, you have level 3 shared cache between multiple cores, right? And this is when you buy the CPU, it's all on board, right? And then everything beneath the last level cache, L3, is encrypted. So there is some hardware piece of silicon, which if you go to memory, you will never see this data unencrypted. So which allows SGX to protect against hardware attacks as well. So if you have some hardware device which allows you to snoop on the memory accesses here for a cloud, for example, right? So that's impossible. And also there is integrity protection. So you can't do replay attack, or you can't really do change any bits of this memory, right? Okay, so that sounds exciting, especially in a cloud setting, because you say, well, sure, now I only trust Intel, so I don't trust the motherboards, I don't trust the cloud providers. I just start my programs in some cloud, and as long as Intel is running, and there are mechanisms, obviously, because SGX also roots into the technology which was previously deployed by Intel, like trusted platform modules and late launch, right? So you have mechanisms for remote attestation, so you can really say, well, actually, by the way, before giving you a piece of data, like my secret data, which enters this enclave, I will essentially ask, are you really running on a real, genuine piece of Intel hardware? And there is a way to attest, right? Say, okay, yes, it's really Intel. Okay, sure. So far, so good, right? So what's the performance of this mechanism, right? So performance is the first kind of warning here, because, well, it turns out that enclaves are not horribly performant, right? Because, okay, sure. First of all, you can't really access system calls of the system anymore, right? Because you're running inside the enclave. but there is no way to invoke the kernel, right? You first have to exit from the enclave into your application and then build some paths to the kernel of the operating system here underneath, right? And here, like, if you want to read a file, you have to go through this part, right? So you have to always exit. And enclave exits are in the order of like 3,000 cycles, right? And you have to exit and then enter back. So like, for example, a simple system call will take you roughly, what is that, roughly 7,000 cycles just to do nothing, right? Intel SDK also at 800 cycles itself. And again, like, not that many people count cycles, but people who build databases, right, we guys do, right? And so normally, on a normal system, a system call is like only like 250 cycles approximately, right? So it's quite a bit slower. But you can say, okay, like, how often do I do system calls? Not that often, because again, I'm smart. I can like read data in large chunks and stuff like that. There are more overheads, unfortunately, right? So first of all, remember this encryption under the last level cache, right? So it comes at a price, right? Because, well, there is some silicon which does this encryption, but really it's still slower, right? So here is the table from this paper by an Israeli team, Elios, right? They measured the slowdown of sequential and random accesses to the last level, to like when you miss the last level cache and really touch the memory, right? So roughly it's like 5.6 times slower for sequential access, same for random access. The writes are slightly more expensive, right? Okay, so you can say, well, sure, like it's slow, but not horrible, maybe. So there is another additional limitation which is worth knowing about. Those enclaves, remember I told you that you have to designate some amount of physical memory for running the enclave. And Intel actually limits the size of this memory because, like, there are probably some inherent silicon limitations or something like that. And they said, okay, look, you can only use 128 megabytes of physical memory, right? And if you load into libraries inside, really you're ending up with something like 90 megabytes of physical memory. If you want to use more memory, well, sure, we'll provide you with some transparent paging mechanism, right? So essentially, you can kind of say, well, you can use all of physical memory, but really like only 90 megabytes will be used, 128 megabytes will be used for real, and everything else will be paged in and paged out transparently to the enclave, right? But unfortunately, this paging in and out is very, very, very slow, right? So it takes roughly 40,000 cycles to do one page fault for this enclave cache, right? And roughly like 25,000 is spent in the like kernel driver, 7,000 exit and entry from the enclave, and like some additional hardware cost, 8,000 K, right? Again, these numbers come from this Elios paper. And you say, okay, sure, like, but what does it really mean for me? Again, I'm building databases. Why would I care, right? So imagine you have 4 kilobyte pages in your system, right? And like, imagine you're managing database records which are like 256 bytes in size, which is not really like unreal. It's not horribly large, not horribly small, right? So if you have a couple of strings, you might up with this size easily. So roughly speaking, you have like 16 records per page, right? On a 4 kilobyte page, 4 records per kilobyte. So you have 4 kilobytes or 16 records, right? And assume you just copy them, or like, I don't know, from one memory location to another. So normally it takes you only like 50 cycles to copy one record. Again, just eyeballing this number, but 50 multiplied by 16, roughly 80 cycles to copy the entire page, right? On a normal, like outside of the enclave. But if you're running inside the enclave, wow, suddenly you see a cost of a page fault, which is like 40,000 cycles, right? So, or you're roughly speaking running 51 times slower, right? So your database suddenly became 51 times slower. Just you put it inside SGX, nothing happened. Or you say, well, copying is just kind of dumb. Let's say how much it will cost me to do a hash table lookup, right? So roughly speaking, you can imagine you know how to build very fast key value stores. So it takes you like 300 cycles to do a lookup, or like roughly again 4,800 per page, right? But again, if you add the cost of a page fault handler, you again running 9 times slower, just out of the blue. And if you don't believe me, again, there are some like macro benchmarks from this Elios paper in which they build a key value store and they compare three different configurations, right? So inside SGX, and it's normalized performance to on like a regular application, and alias accelerates SGX. Okay, let's forget about alias here, but let's just look at the yellow part for now, right? So first of all, if everything fits in a 2 megabyte cache of the CPU, you're just running 10% slower, 10 times slower, sorry. So meaning that it's a key value store. Normally it takes you only 1,000 cycles per key value request, but suddenly it takes you 9,000 cycles, right, roughly. But it's still in last level cache of the CPU, just slow down right there. If you still fit in this enclave cache, right, 64 megabytes is your data set, you're roughly like at 12 times slower, right? So still slow. If you suddenly use paging and start paging out of the available 128 megabyte memory, you're running 33 times slower, right? So what it means is that even if you decide building databases for SGX, you have to be careful. You have to be clever as alias, right? At least, or more clever to make sure that you eliminate all of these page faults and you like somehow optimize your data and memory accesses to make sure that, okay, you know, like you at least approach the speed of unprotected applications, right? So are there any questions about performance right now? Because I will switch to the security, because my main part is really security, not performance. But if there is anything to ask here, it's a good point. Okay, no questions. Good. So let's go forward. Okay. But of course, like no matter whether you run slow or fast, you at least would expect that, you know, SGX provides some degree of security. After all, Intel deployed it for you, right? So, but the answer is that in practice, SGX provides no security whatsoever, right? That's the major kind of conclusion we're trying to make. Okay, what went wrong, right? After all, like Intel promised us, you know, like tiny bit of silicon, and only the code which you put inside the enclave is your trusted computing base, right? So everything else is outside. So how can you attack this system to begin with? The problem, like the fundamental problem in this design, which SGX essentially followed, is that the fact that attacker can control the operating system or the tower of virtual machine monitor plus operating system creates a very powerful attacking model, meaning that for decades we knew about side channel attacks, right? But they were kind of benign. So like once in a while someone was attacking an RSA library, and RSA came up with some, you know, oblivious techniques to make sure that, you know, cache accesses are hidden, right? But it was hard because attackers were not controlling the operating system kernel, but in SGX, attacker can do whatever it wants with the operating system, and essentially it can control the enclave. This model is so powerful that you can come up with techniques which allow you to essentially single step the SGX program, right? Essentially, you don't know what's running inside, but you can create conditions by like changing the operating system slightly, which essentially allows you to execute one instruction inside SGX and then preempt the execution and observe the environment. And you say, well, but how does environment changes? Well, but you can suddenly launch all these side channel attacks like cache level or page level or branch level attacks, right? And see what is happening, right? So it's extremely powerful model. And of course, attackers are smart. They had decades of practice on side channels, but suddenly, you know, everything like, you know, like now we can attack clouds, right? So that's cool. So effectively, every speculative microarchitectural mechanism of a CPU was attacked, right? So branch target buffers, there's a couple of papers here. Pattern history table, yes. Caches obviously was attacked, like everything is a side channel. DRAM row buffer, page tables, page fault exception handlers, speculative execution itself, right? So like it turned out that CPU designers were totally not ready for this amount of side channels. And if in the past those side channels were barely practical, with SGX, well, they became very, very practical because of this powerful adversary model, who can control the entire operating system. So, okay, let's do a slight detour into those attacks. It's like, again, in order to protect our databases from those attacks, we need to at least understand what's going on. And some people, of course, know this, right? So it's nothing is new here, but let's just give it some overview. So most kind of like the oldest attack out there is the attack on the page fault handlers, because remember, SGX is running on top of the operating system. Well, the requirements for backward compatibility forced Intel to take a pass on of leaving the page fault handlers under control of the operating system. So essentially, the operating system can say, okay, sure, I will write protect a page. And the moment the program inside the enclave touches the page, well, it will trigger a page fault. And okay, can you use it to do something? Okay, sure. Like imagine you have a page X here, which contains this if statement, like, right? So, and it depends on a secret input, right? And depending on like whether the input is true or false, right? It jumps to two different functions, right? Maybe it executes like function 1 in your database or function 2. And if you're lucky enough, those functions are on two different pages, right? Pages of memory. I mean, because I didn't go through the entire kind of paging infrastructure, but at least we can understand that something is happening, right? And you say, well, sure, is it powerful at all? Well, it turns out it is powerful, right? So you can also like construct sequences of those page faults, right? So for example, you say, well, first I've seen a page fault on page X, then page fault on page Y, right? So you have a sequence of X, Y, and here you, for example, have a sequence X, Z, right? Okay, so what can you do with it? So imagine you say, well, I'm running some application, like, I don't know, like a text editor, and of course, it uses some kind of a spell checker. It's kind of not uncommon, right? We all run spell checkers because we can't really write anymore without them, right? And this specific spell checker is called HuntSpell, right? It's just a library, but it's illustrative, right? For the purposes of this attack. What it does is that it sucks in a dictionary, right? And inserts words from the dictionary in a hash table, right? And then, okay, insertion is deterministic because the attacker assumes that the dictionary is the same. That's true, right? And you say, sure, like I've seen a page fault in page 1, then a page fault, for example, in page 5, right? Well, you create those when you start the attack, you observe this, like you launch a dictionary, you know which word triggers which page fault sequence, right? And obviously later on, when you observe execution of this program, which a person is running, right? You can reconstruct the page fault sequences. So here, for example, it's page fault 4 and then page fault 7, right? So it leads you first here and then immediately here. So you have a side. You can conclude that the word which was accessed was side, right? And then you say, well, what else? Like 156 give you channel, right? So 1 and then page 5, and then it's an overflow because there's like the page table, like there's a collision, so you overflow into 6, right? So that's a channel. And it wasn't like, sounds a little bit naive, right? But it was in 2015, so don't worry. The attacks matured in complexity a lot, right? So here is an example, right? So they were able to reconstruct Wizard of Oz with 96% accuracy, right? And it was using this infrastructure from Microsoft Research, right? So SGX Haven. Similar, you can say, okay, sure, these hash tables are easy. What about anything else? Well, JPEG, right? So, like, can you reconstruct images which are processed in SGX, right, inside the enclave? Well, what SGX is doing internally just splits the image into this 8x8 bit blocks, right, which are colors, just does some transformation on them. And this function is like, here it's on the right, on the left here, so it fits in one page. So you say, wow, can I even like do the page fault attack here? Because, you know, like you will be always faulting on the same page over and over. But you can say, okay, sure, but if I carefully look at this code, I can see that there is this optimization here, which says, okay, by the way, if the line of this 8x8 thing, if the light is 0, well, don't do anything, like continue here, right? So kind of you, instead of like following like, or doing this this complex computation here, you just jump out, and what you can do here, you can start counting how much time, how many page faults you were actually seeing, right? So for example, if you're doing a string length function, and you remember you have this very powerful framework which allows you to single step the SGX enclaves, and you can, like if you're doing a string lang and you assume that your code essentially loops and accesses every character of a screen, so you will see the number of page fault, which is proportional to the length of the string, right? So it's similar here with a page fault. So you kind of say, okay, sure, I can't really see the image, right? So there is no like jumps between the pages, but I can at least like distinguish 0 whether it was this line, and it turns out to be in practice quite often versus once, right? And what the images look like is, well, first of all, you can reconstruct different colors. Typically you have like 3, red, green, and blue, right? So, well, if this is an original image, you have this wonderful, tiny, reconstructed image. And, well, like kind of privacy is lost here, right? So you see what's going on inside. And like you have different examples, like real white, black and white kind of images, and like real full color images, and you still can understand what's going on, right? So that kind of should scare you, because you show like, well, you can say, okay, yeah, we do process images in databases, so clearly something is happening there. Okay, so that was just page level attacks, but can you do more fine-grained attacks? The next, obviously, set of classical attacks are cache line level attacks, right? So the technique is called prime and probe, but there are like multiple flavors of this attack. The idea is that you can monitor cache line accesses. So now your granularity is not the cache, not the page, pardon, which is 496 byte, but instead the individual cache lines, which are 64 bytes long, right? So your resolution increases, right? So what happens here is that, okay, sure. So the attacker here first primes the cache. So essentially, like, it puts its own data into the caches, right? So essentially by accessing them frequently, right, and like accounting for collisions and whatever, the sets and stuff like that, but it fills the entire cache with its own data. And then it runs the victim, right, the enclave. And the enclave, like, again, like depending on some bit and some number, and it can be your RSA key, for example, bit I of this RSA key, it maybe reads line X or line Y, right? So, and in this example, well, then part of the branch is executed right here. So this cache line was touched, right? And essentially the attacker's cache line was evicted from the cache, right? And I mean, the resolution and like performance of this attack depends on what level in the caching hierarchy you like kind of attack, right? So you can say L1, L2, or L3. But remember, like, if back in the days you didn't have control over your cloud, right? You was hoping to be collocated with a virtual machine of your victim, right? So now you have full control over your operating system, right? And you really will be mounting this attack on L1, right? I will explain in a second how it will work, right? So, but okay, so the victim replaced this data in a cache, and then attacker again, since remember single stepping, so we do one round of like maybe executing just one instruction in the victim, but then let's again measure the cache line accesses, how long they take. And there are mechanisms on Intel which provide enough resolution to essentially either measure the time, how long it takes to access the cache line, but of course, and it works for something like last level cache because it's roughly like 50 cycles to access last level cache. But the first level cache takes only like 2-3 cycles, and those timing mechanisms are not available, but Intel gave us another counter. So it's hardware performance counter, which counts the number of cache misses, right? And here you can like essentially like access this line, read the counter, access this line, read the counter, and so on, and figure out that, okay, here there was a miss, right? So it's a very high resolution attack, right? And again, so again, I was saying that you control the entire operating system here, right? So you say, well, I will create a very carefully designed environment for my victim enclave here, and my prime plus probe code which will be attacking this enclave. Specifically to amplify the resolution of this attack, I will put them on the single core, right? So it's core 0, core n. So you have a multi-core machine here, but here you have multiple hyperthreads, thread 0 and thread 1. So you change the scheduling in the system saying, okay, everything else moves outside, right, and runs elsewhere. Only this enclave and my attacker code, prime plus probe, runs on those two hyperthreads which share first and second level caches, right? And there are some additional tricks, right? You know, like I told you, like performance monitoring counters. If you want to interrupt or preempt the attacker single stepping style, you can also configure the hardware timer, and it will be essentially preempting, like letting, like the timer itself can take you 170 cycles to execute, but you can always play with evicting virtual to physical memory translation entries from TLB. It's like a cache which caches those translations, and then you know your memory instructions will take a long time, and then the exception will be delivered right after that, for example. So that became really practical. Like just 2 years later, this attack is already there, and they like demonstrated attack on a very practical framework, VC3, which is a MapReduce framework, which Microsoft Research built for running in SGX. And what's interesting here, they don't even assume the knowledge of the user functions, user map and reduce functions. They only assume the knowledge of the framework and the fact that framework will be using words for doing the reduce. So something, if you like doing something like a word count, you know, like your framework itself will hash the word, and by observing the hash function, you can, remember, conclude the word lengths, and by observing which cache lines were touched when these words were inserted in a hash table, you can also conclude where it went in memory. So you can have some information about actually the hash value of this function, right? So what do we have here? So I still have time. Okay, yeah, they told me that I should like kind of speed up a little, but yeah. So
can I ask a quick question? So
yeah, go ahead, go.
What if you have more complicated functions compared to word counts and that you showed in the previous example? Would the proposed control execution work in these cases?
Right. So I believe it will, because imagine we're attacking databases, which, well, like first of all, we'll have some code like this, right? If and else. And like it's very hard to write code without those, without this like logical blocks, right? I will talk a little bit about whether it can be done, but I think in many cases it's possible. I mean, my goal was obviously to kind of like convince you by examples from those papers that it's possible. If you're not convinced, yeah, let's take a look.
Okay, please go ahead. Yeah, maybe we'll cover it later.
So Sharad and Shantanu, so you were texting me saying that how much time do I still have? No time already?
Negative 10 minutes, but that's okay. I think it's interesting sort of.
I think I want to ask a question, basically, if you are stopping this attack discussion, which is, given I follow some of the attacks over the years, so which of the existing attack landscape against SGX can be preventable by now? I mean, did they fix some of these issues, or especially, I mean...
I kind of say no, nothing is fixed.
Okay. So basically, if you use SGX, even if whatever you do as the developer, imagine I use the best available, whatever ideas like ORAN, this and that, whatever I do, SGX is insecure as of now. Is that what you are saying?
Yeah, so let me kind of move a little bit forward, and then hopefully I will be able to answer your question. So obviously I thought that I will be going a little bit faster, and now, okay. So I will skip over this section. Okay, so in this slide, they were reconstructing with this MapReduce, the Wizard of Oz again, like you can see that, okay, it looks like real text, right? So they didn't manage to reconstruct it. Another interesting thing is that you can also observe not only cache line accesses, but taken and non-taken branches, right? And obviously, in my previous example, I was saying something like this, and then touch a cache line here, right? But it's better than this. So imagine we have seen something here like if a equals to 0, then take a branch and then else, and maybe you're touching the same cache line, right? So you kind of say, wow, the cache level attacks are no longer possible, right? But it turns out that you can observe the branch predictor and launch an attack which allows you to trace taken and non-taken branches. Essentially, if your code takes a branch and it's secret dependent, you learn something about the secret, right? Again, sorry, unfortunately, running out of time, but this is one of those algorithms which kind of is designed, one of those examples which are designed to convince you that, okay, it's not really secure. So that's part of the RSA encryption algorithm, right? And it has like a couple of branches here marked with stars, right? And what this branches depends on, it's bit of an exponent, right? Well, you say, that's kind of scary already. And what they do is that they can recover 66% of 1024 RSA key from a single run, right? So it's kind of scary because you say, well, I observed the enclave running only once and I get 66% bits correct. And they recover the full key from 10 runs. Again, I encourage you to read those papers. They're kind of like easy, right? Easy read to a degree. And you say, well, like, can I come up with a more secure code to kind of avoid this attack? It's not easy, it's possible. Okay, possible defenses. Sorry, again, let's speed up a little. You say, wow, can I do anything? And this is where it becomes interesting because it kind of like gets into this question whether what is fixed there. You say, well, can I build a database without a single if statement? And the answer is yes, you can. It will take you some time though. So you can start using oblivious primitives. So here, for example, I have a max function, right? And this is a non-oblivious function because it has a branch, right? Which is observable, right? Remember, we have this branch tracing attack. I can rewrite it with these two primitives.
Hello.
Yeah, is there a question?
Hello.
Yep. Okay, no one is there, right? So negative 10. Anyway, so it turns out that you use these conditional move instructions, right? Which essentially allow you to either do a move from register RDX into RAX based on whether the logical flag is set. And you can implement something like max functions, or you can access arrays in a totally oblivious manner, meaning that your code suddenly doesn't have a single if then else branch, despite the like a big loop, which is, depends on the size, which is public typically for databases, right? And well, you also access, for example, if you have an array here, right? So I have it on a different slide. So instead of like accessing element I of the array, you have to really access all of them. And only one of these accesses will be using this conditional move instruction, which really moves your data into the register. And the rest are kind of concealed from the attacker, right? And okay, there is a great paper for this like oblivious multi-party machine learning engines from Microsoft Research again, which kind of uses those primitives. They are not entirely new, but like at least it's kind of a fresh look at them. And you say, well, sure, now I really have to rewrite all my database. So like, because everything what we know, right? You can't really access records anymore, like based on I, right? So because it reveals something about your database, right? So if you want to access I, you have to access all of them, which means that, for example, well, you can't do sorting because sorting is input dependent, right? Something like quick sort, right? So instead you have to use something like a parallel bitonic sort, right? Which irrespective of the input touches all the records in the database in a deterministic manner. And you say, well, sure, what's wrong with bitonic sort? Well, the square is long, right? Because instead of n log n, it's now n log square n, right? And what does this square n means? Like if you have 1 million records in a database, well, this is 20. 10 millions, this is 23. So roughly speaking, you're like 20x slower, right? That's kind of bad, but possible, right? So you say, well, I will rewrite the entire database in this oblivious fashion, no branches, no like early stops and sorting. Like you, by the way, can't use hash functions because, you know, like again, it's input dependent, right? And the question is like, to really answer your question, what will be fixed, like essentially, because we started seeing the databases which are kind of saying, okay, we're going to run inside SGX, but are they really secure? Well, to a degree, right? So what will get likely fixed? Like today, nothing is really fixed, right? You have some micro-architectural patches which fix like the most brutal SGX attacks when, you know, like SGX memory is just plain text dumped. This is fixed by Intel, right? It's called like L1 terminal bug, right? So that's done. So now SGX is kind of like, again, semi-secure. But you know, cache level attacks are not fixed. Like there is no solution from Intel. You can use partitioned caches and maybe it will help you somewhat, but really no. Unless you're running on some dedicated piece of software which partitions caches underneath you and somehow disables those attacks, you can't do that. But that's not the case. Attacker controls the operating system, right? So branch predictors are not fixed and will not, like, maybe they will be fixed later, but you have to partition branch predictors or flush them, right, when you exit and enter SGX, which will result in more expensive exits. There are some like crazy architectural ideas which say, wow, sure, we will fix everything, but it will take us decades or like multiple decades to get them implemented in practice, right? And moreover, those paging attacks, well, unless you change the entire software stack and you say, wow, it's a radically new SGX, which doesn't have operating system underneath, they will remain, right? There is no way to say, wow, this SGX memory, like I was saying, that SGX caches, last level cache, will likely be protected with partition caches. But SGX memory, this 128 megabytes, will remain open forever. So if you say, wow, if attacker can observe page level accesses here, then you're open for the attack. So your database should account for that, right? And you say, well, yeah, sure, maybe there will be something like an ORM in hardware, but this is like 10 times overhead, right? So it's unlikely to happen, right, in the near future. So today I would say, and this is like kind of the main message of this tutorial, SGX is, it provides some protection, but it's not a bulletproof protection. You really have to invest in this software hardware co-design to make sure that your code is fully oblivious, and then, you know, SGX can be used as a security mechanism. But if you don't do this, then essentially there is no protection. Okay, so I think I'm done here just for the sake of time, and I'm probably handing the mic back to Shantanu. And I hope there will be some time for questions a little bit later.
To Sarath. Now Sarath will directly conclude this.
Shantanu, say again.
I am saying that now give the control to Sarath.
Oh, sure, okay.
Yeah.
Stop sharing here.
Okay, so all right, I think we are going to the last phase, and we'll try to save a couple of minutes at least for questioning, and yet try to manage on time. Let me share my screen first. Let's see, where were we? Just one second. Okay, what's the feature? I think we got there. Just give me 1 second to share my screen. There's the share screen. It's right here. Question, where is? Which is the thing, I guess.
Share screen.
Oh, this one, sorry, got it. Can you see it now?
Yeah.
Yep.
Okay, well, I have to go to that myself first for a second, just so that, okay, and then to presentation mode. All right, so I think we've gone through a variety. We started off with a problem which has been open for 20 years. We've sort of seen the move in cryptography and so many different attempts in trying to solve the problem of encrypted data processing and security while outsourcing. Then we looked at SGX's evolution, how it came around. Let me see if let me go to the right. Okay. Yeah. So, and then we saw the evolution of that towards SGX and its utilization for trying to build basically database technology. There have been attempts, as we note, as Anton pointed out, towards doing this for MapReduce and for databases. Now we're completely out of time, so we will not go into it. Like Shantanu had prepared some very nice slides summarizing the work on Opaque, which is one of the first systems to have sort of gone beyond and tried to do joins as well on SGX. And they limited themselves to foreign key joins, but we're not going to go through this approach of it. But any of these approaches, as Anton points out, is sort of suffers from basically leakage and also performance overheads. When you try to overcome the security, at least some of the security aspects of it, then it basically ends up having a significant amount of cost. So these systems are finally all not secure in that sense. So there's a lot of rich stuff to be done, both from an architectural perspective as well as database perspective, and maybe a combination of the two, sort of trying to work together towards a solution which is actually tenable. That will be interesting. I think the final note of the approach, and maybe we'll end with that, is for a while to come, there is going to be, it appears, no silver bullet again. There's a significant amount of interest, I think, in a variety of different companies working on products which relate to essentially secure data outsourcing. These are at startup level as well as companies like Microsoft. Actually, some of the folks from Microsoft are here in the tutorial. They could probably tell us better as to what they're doing. We don't exactly get to know it, but I think Ravi is here, for example. So Ravi might be able to shed some more light on that stuff. I know Raghav has been working with the SQL Server team
So
for a while now.
I had a small comment, Sharad. So
Sure.
the cipher-based original prototype used an FPGA, but
Correct.
SQL Server has actually shipped a version of that using SGX.
Perfect.
The latest version of Always Encrypted is shipped using SGX. And this is now public, so I can share it freely. And we have a Sigmod industrial track paper on that coming this year. So whatever we did in cipher-based, some fraction of that, only for PII data. So we can do like range predicates and like predicates, pattern matching, but we use SGX. So
Yes.
that is
Yeah, I guess so. I guess that was the case. But yeah, that makes total sense. So I think there is cipher-based, by the way, was an excellent sort of papers to read in terms of initial thoughts of how, I think I mentioned that already, of how to go around sort of using secure hardware. Now,
and I think another advantage of cipher-based is since the FPGA is a separate circuit, all these side channel attacks doesn't exist.
Yes.
Because we fabricated our own circuit, and SGX versus FPGA, that is the trade-off. And maybe Ken can talk more, but that was the advantage of building a separate circuit, and it has no side channel attacks. It has no link to the operating system, nothing. It's just hardware. So
I'd say it's a little bit too strong of a statement to say there's no side channel attacks. There's different side channel attacks.
Yeah, true. But at least the ones that are studied for SGX. There's no cache line.
Right. With regards to that, yeah, you're right.
Yes. But there is this obliviousness that you have to implement, which has extreme overheads in reality as well, right? So
it's not correct. We implement, this is more at some, depending on the situation, like some of the things are by default oblivious operations. So I think if you carefully implement obliviously, overhead may not be super high. I'll share the paper.
Okay, that would be certainly interesting. So the better known sort of system right now, at least, like, and this is the comparison graph which I wanted to sort of re-bring back again. In terms of processing, there is overhead significantly for secure hardware. Now, obviously, it's a huge area where a lot of people are working towards it. So our sort of experimental evaluation is that if you start doing anything reasonable, you pay to the order of 3 or 4 orders of magnitude over clear text data in SGX. Now, Murad, I'd love to see if there's work from your side, which is sort of showing this.
I mean, basically, we haven't done, it's a CCS paper 2 years ago. We haven't done the database, entire database. It was about like machine learning and other type of data analytics. So we tried to do
I think a lot depends upon the size of the data that you're dealing with and how it fits.
We didn't do distributed. Yeah, so we assume single machine.
I see.
Yeah.
Well, anyways, I think this is a hot area. It's sort of interesting to go forward with. Let me offer one small solution possibility, which we are thinking in terms of addressing the complexity of, let's say, trying to get to work with a variety of different technologies. And I'm not sure how this will go and where this will go. I'm not going to go into the technical details of it, but this concept of, let me skip through the slides and go to maybe this slide, right? So I started sort of with this slide. Let me end also sort of with this slide. So if we can exploit the fact that somehow users can participate in sort of differentiating the needs of, mostly from a semantic level, of the security needs that they have on data, we can probably design techniques which are sort of more scalable in this situation. In other words, I can offer higher levels of security for data which is extremely sensitive, while I offer less level of security for data which is not sensitive. The question is, can we make a formal statement of it? Can we sort of do this in a way where the guarantees that we are getting are maintain some level of provability to them? And that, I think, is an interesting question which we have not fully addressed. And I think it's an approach which one can possibly explore. The advantage, the reasoning why that thinking seems like an interesting mindset to me is it's rooted very much in data management, because in data management, we sort of think of operator level optimizations. We sort of think of abstractions and partitioning of computation, whether we have dealt with distributed computing, whether we have dealt with, whenever we dealt with distributed computing for that matter, or in the past when you're dealing in with outsourcing of data, we started the projects and work in this direction of partitioning computation across different places. So it's a very data-oriented sort of a concept. And actually, even if you go back to the thing that Shantanu presented on Conclave, that's also a reflection of something similar, because the whole idea of Conclave and how to make MPC scale is to use operationalize it, or whatever, operator-based logic, and sort of push down and push up of the operator. That's sort of what Shantanu was sort of emphasizing. This is also something which has been seen in cipher-based as well, in the context of, let's say, executing on secure hardware in the FPGA. I think it's a technique which is natural in this domain. Then you have heterogeneous computational sort of environment. Now, the key question still remains: can I really sort of put strong guarantees? And I understand this is very vague right now because we didn't get a chance to sort of explain what we had in mind more properly. But this concept of trying to at least partition computation and provide provable guarantees of, let's say, how to execute in this different whatever, like when you store stuff in different, let's say, systems, and enable based on the requirement from the end user. So I thought I'll end with that and skip through all the other stuff, and maybe there's, let's see if we had a final conclusion slide. Well, the paper that I'm referring to, which sort of builds a case for this, is in last year's VLDB. Oh, sorry, last year's ICDE on partitioning computing. It's co-authored with Shantanu and with Jeff Ellman and a couple of other students. So if you're interested in that, you can sort of have a look at that. And I think the last slide was essentially just that we are probably, this slide could have been drawn 20 years ago. It still is relevant. 15 years ago, there are lots of different solutions which are trade-offs between functionality, security overhead, and so on. So like Shantanu has done a good job of sort of showing a three-dimensional sort of a figure into two dimensions, or two-dimensional projections of functionality and security and overhead and security. And so these techniques remain. So there's a lot of work that's still happening, both in the research community. People are discovering new techniques all the time. And there's bright future. I think it'll be interesting to see how the secure hardware plays out. There's also exciting work, which I should mention, Sanctum, which is happening at MIT. I'm not totally sure what the state of the art there is, but some of the faults, I think Jana was asking, I think, about this, right? So somebody asked the question on that stuff. So Sanctum is another project which is going on, which sort of takes care of some of the hardware, some of the problems that are faced by SGX. So I think I'll stop at that. And Shantanu, do you want to have any concluding thoughts, or Anton, do you have to have any concluding thoughts? Then we can open up for 5 minutes of questions, maybe.
Let's go to questions.
Okay, and Murat, you can have you could be a co-author on this thing, on the tutorials. You can have a final question too, or any, or even Ravi.
That's what I was trying to ask Anton, because basically some of these SGX attacks get all these sensitive keys, etc., in the enclave, even if you do ORM and so on. So I think he answered that, saying that some of those could be solvable, not solved yet.
Yeah.
Right, with the Intel updates, but the memory access patterns will always an issue. So I think for designers like Cypherbase and all of us, I think we may need to go into a ORM world and try to make it more efficient, I guess, for data-specific tasks, maybe. Also.
Well, it looks to me that oblivious computations are faster than ORM, because even the fastest ORM implementations in hardware are still 10 times slower than regular. So this way I would go with oblivious. Maybe those side channel attacks are easier to fix in software and hardware than just saying oblivious ORM. It's still an open question. Maybe you can design algorithms which are faster with a RAM versus, you know, when you crunch through all the records with bytonic sort, for example.
No, I was referring to oblivious computation, not ORM. I'm sorry, I'm mistaken.
Okay, got it. Yeah.
Carefully designed oblivious computation. Yeah. Thank you.
Any other questions or comments? If not, maybe we are actually out of time. We are well beyond time. I'm not sure how many people are still there on the session here. People left, or let's see.
No, everybody's still here, but I do think that people may have other things scheduled.
Yeah,
So.
no, of course, that's why. So we need to finish maybe last question or something. I don't know. Ken, do you have time for one more question, or should we end now?
Maybe we're already 5 minutes over, so maybe we should we should
Right.
call it.
So to be continued, there is a Slack channel. If there are questions concerned, Ravi, I would love. But let me just say one more quick pitch. Ravi, I'd love to hear from you about the SGX implementation of Always Encrypt. Maybe we can follow up separately on that.
I'll send you a link. We can follow up on that. Yeah.
Perfect. All right. And slides
Great.
will be available, I think, soon. Like we'll collect all slides from Anton as well, we incorporate them and send it out. Maybe on Slack channel we'll send out when I'm sure the conference will take care of it, hopefully.
Yes, I think they will.
I will email to tutorial chairs and I will put on Slack channel. So
Thank you, everyone. Thank you. We appreciate your coming to the talk or coming to the tutorial. Thank you.
Oh, well, thank you, Shiraj, Shantu, Anton. You know, this is a really complicated topic, and I think there's a lot of room for exploration. So, you know, just thanks for putting this tutorial together.
Thank you.
So just some
Thank you very much.
housekeeping. So all the sessions are now going to take a 30-minute break, and the room for Dr. Kupa's overview of the Department of Computer Science at UT Dallas is going to open 5 minutes before the session is scheduled to start. To get a link to that virtual room, please check the conference website. So thanks everybody for attending.
Bye. Thank you.
Thank you.
bye.